Hello guys, my name is Ahmad Wildan bin Mazani. I am one of the group member of Project COA.
Assalamualaikum and good evening. My name is Muhammad Adam Ashraf Zamri and my metro number is A24CS0119. Today I will be presenting about CPU performance, which is benchmarking result, analysis, comparison and discussions, and the personal reflections based on the data collected.
Assalamualaikum and hi everyone. My name is Alif and I'm one of the group members for this benchmarking project. And in this video, I'll be explaining the mini tools, this benchmarking result, and the assembly language coding and the result for part 2, and end with a brief reflection.
Hi, my name is Muhammad Hafiz bin PE. This group project is to assessing CPU performance of computers through benchmarking tools. Benchmarking is one of the ways to test and evaluate every aspect of this computer's capabilities. The problem that we found is most of the users are lack understanding of their device capabilities. So benchmarking helps them to evaluate, analyze, and identify the details of the device performance. So the aim of this group project is that to evaluate and compare CPU performance using free benchmarking tools and assembly programs. By analyzing how the CPU of each device handles under the different loads and operation, the result will provide details of the processor efficiency, system responsiveness, and hardware limitations. The objective of our group project is that to understand the concept of the CPU benchmarking, to compare the performance of different CPUs, to analyze the impact of different workloads on CPU performance, to learn to use free benchmarking tools and interpret their results, and to implement an assembly program to simulate CPU load and measure execution time. So the scopes that we are looking for the computer specification is that the CPU processor, cache, memory, motherboard, and disk type. And the tools benchmarking that we use are CPU-Z, Geekbench, Windows Task Manager, and Minitool Partition Wizard free.
For, for computer A CPU Z result, we have that shifted information, CPU information, where it stated that this processor for CPU for computer A is Intel Core i7 7650H, and then we also have the core speed around 1000 megahertz. Alright. Next is Geekbench Computer A. So the score for Astro AN 51548 is 8172 for multi-core score, and for single core score is around 1594. For computer A, many tools we undergo the sequential test. So for this one, we already uh, read and uh, it will show that transfer status for sequential reading in here, and then for random it also show that transfer status like this. For task manager computer A, first we undergo the low CPU load. For the usage of memory is 46%, and this is the performance how the graph happen for the CPU load, and this makes CPU load around 50 to 60% memory usage. So this is what the application tools use. So the performance is slightly higher from the previous low CPU load, and this is the highest one, which is above 90%. Alright, the performance graph already almost nearly achieve the full memory usage. And then we end the task that uh, very play a big role in the 90% above consuming memory. So we end in the opera, and the output, the memory performance drop down suddenly after we close the opera.
So now let's move to computer B. One of the benchmarking tools we use is CPU-Z, and here we can see that in computer B, we have Intel Core i5 1240p, which is 12th generations of Alder Lake. and its base power is 28 watts, and the cores is 4 performance cores and 8 efficient cores, totaling 16 threads. Next, we have Geekbench. As we can see here, the single core score is 1935 and the multi-core score is 6591 score. And it shows that this computer is less multitask than computer A. And the next one, we use mini tools. This is a sequential result, and this is the random result from mini tools. And last, we will go through task manager. This is low CPU load. So we can see here, the memory we use only 47%, and as you can see here, the line only 47%. So next we have mixed CPU load. Basically, it increased because we already opened some of the applications like Steam, Discord, and the games. So it will increase to 67%. And this is the memory in the performance, and this is hard CPU load. We already opened Google Chrome, Microsoft Edge, Spotify, and others. So it shows that the memory increased drastically, which is 94%, almost full. And this is for the performance. And so after we close Google Chrome, we can see that the memory drastically dropped from 94% to 57% because the Google Chrome holds the most memory, so it will make the computer become faster. This is the performance.
For my part, I tested on the computer C. This is the result of benchmarking using the CPU Z. And these are for the Geekbench, using the Geekbench. And then using the mini tools, this is the sequential section, the random section, and last but not least, the task manager. The low level load for the computer C is 50%, and then the middle level load 77%, and the high level load 86%. And then I try to make the memory load to be 90% above, so this is the result. The most consumed memory is the Google Chrome, and then I try to release the most consumed memory, and then it reduced to 70%.
So now I will explain in detail about computer A. Computer A built with Intel Core i7-12650H is a powerful 12th generation of the late CPU. It will help the computer to handle high workloads, and its architecture of 6 performance core and 4 efficiency cores offer excellent multitasking performance with 16 total threads. The CPU has a normal clock speed of 2.3 GHz and can go up to 4.7 GHz when you run multi applications. And it also have the massive 24 megabyte of L3 cache, which significantly enhance performance for big data sets and applications with high demands. Computer A supports DDR4 and DDR5 memory, offering flexibility for a variety of CPU configurations. And last but not least, it uses 45 watt TDP and compatibility with the FCBGA 1744 socket. And next, we will go to Computer B. Computer B built with Intel Core i5-1240B that provides a balanced performance and efficiency 12th generation of the late processor. It is built with 4 performance core and 8 efficiency cores. It total up to 12 cores and 16 threads. It makes it suitable for average workloads. We have a base clock of 1.7 GHz and a turbo boost up to 4.4 GHz. It provides a high performance for everyday computing needs. And the CPU includes a 12 megabyte L3 cache, which is half of the i7, but still sufficient for every applications. It also supports DDR4 and DDR5 memory, ensuring a good memory for bandwidth for multitasking. And Computer B has a lower 28 watt TDP, making a lightweight laptop that requires a balance of performance and battery efficiency. And it supports FCBGA 1744 socket. And last, we have Computer C. It built with Intel Core i5-1335U. This is a power-efficient 13th generation Raptor Lake processor. It is designed for light laptop and portable device. It has 2 performance core and 8 efficiency cores, and total up of to 10 cores and 12 threads, all geared for low power consumption while maintaining performance. And this computer also have an average clock speed of 1.2 GHz but may increase to 4.6 GHz, enable fast performance for light applications. And computer C has a 12 megabyte L3 cache, which improve efficiency due to current versions. And the computer B support the same DDR4 and DDR5 memory, and it has a 15 watt TDP and support FCBGA 1744 socket. When we compare computer B with others in our group, if A use something like an i7s, both CPU are similar in architecture, but however, A might win on raw multi-core performance due to higher TDP and larger cache. But computer C, it has the latest generation i5. In that comparison, computer B outclass it in every way: higher core, thread counts, higher IPC, better instruction set, and more cache.
We have Geekbench for Geekbench CPU stress test. Alright, we have Geekbench CPU stress test. Firstly, the overall analysis show that computer A is the best overall in multi-core performance. It's the top choice for developers, creators, and power users. And the computer B is strongest in single core, ideal for users prioritizing fast interaction, office tasks, and light multitasking. And the computer C is balanced, but scores lower overall, suitable for general use or budget systems. So as you guys can see, the score of overall for computer A in multi, it shows that clearly show that it is very far from the other multi-core score for the other computers. So what happened is multi-core is very useful for them, for developers, creators, and for users. And computer B is suitable for office workers, and computer C is for general use. Everybody can use. If you go to like low budget system or low budget uh low CPU task, you can go to computer C.
Jump to Minitool Dash benchmarking table. For the disk performance benchmarking, we use Minitool partition wizard to test both sequential and random read-write speed at different transfer size. We test three different computers, which is computer A, B, and C, all using HDD or SSD drives. For computer A, using 32 kilobyte transfer size in sequential mode, it achieved 1783.7 megabytes read speed and 3749.33 megabytes write speed, while in 4 kilobyte random mode, the read was 1036.48 megabyte and write was 941.39 megabytes. And for computer B, it had higher sequential rate of 1978.34 megabytes, but a lower write speed of 1211.14 megabytes. And in 4 kilobyte random mode, its performance dropped significantly to 375.58 in read and 221.01 in write, indicating weaker performance in random access. And lastly, for computer C, it recorded 1203.44 in read and 476.29 in write for sequential mode, which is 32 kilobytes, and 450.64 in read with 307.76 in write in random mode, which using 4 kilobytes. And from all of this, we can see that sequential mode generally perform faster, but the result also depend on the drive hardware and optimization.
So these are the benchmarking result using Task Manager. As you can see, these are the comparison for each computer A, B, and C. So each of the computer on the low loads level share the same result, which is having smooth system. And then as the memory increase to the middle load level, all the computers become slightly lag as it runs multiple tasks. And then on the high level load, the system of the computers become more laggy and slow responsive time, and then have the fan noise.
For part 2 of the project, I developed an assembly language program to simulate CPU load. The program runs a loop that calculates the polynomial equation of y equal to 22x to the power of 3 plus 9x to the power of 2 plus 7x plus 30. It uses the get and second function to measure how long it takes the CPU to complete the loop. I run tests with different loop counts. So as you can see, beside the table, this is the benchmarking program result. So for uh, loop of 50, the CPU time was 755 milliseconds. At loop 100, it increased to 1539 milliseconds. For 200 loops, it reached 3093 milliseconds. At 500 loops, the time was 7797 milliseconds. And for 7,700 loops, it was 10,870 milliseconds. And lastly, at 1,000 loop, the CPU time was 15,499 milliseconds. This showed a consistent linear increase in execution time, proving that the CPU was working harder with each larger input size. The 1 millisecond delay in each iteration helped simulate stress and make the timing measurable. So this is for the ASM benchmarking code. For the first part, where the data part is, we basically initialize some string and initialize some data. And for the code part, here where we basically print the string for user instruction, and here where we call get msecond, where it will capture the current time when we execute the code. And here basically for polynomial calculation codes, where we calculate the calculation, and here are where we display the results. And lastly, when we press Y, it will repeat the whole benchmarking program.
All right. The conclusion is in part one, we already use the benchmarking windows for PCs. We use three PCs. Okay, the first three tools we use is CPUZ, Geekbench, and then followed by Magic and Minitor partition result. Next, we already test on every PC for low, medium, and high CPU and disk loads, and we collect data on processing speed, memory throughput, and disk input output. We observe clear performance gaps tied to hardware specs and workload stability. And in the part two, for assembly language performance test, we already would optimize 86 assembly code, and then we delay the coefficients were based on team members there for variety, and then we measure execution time for different loop counts with event 32s, and then event 32s get seconds, and then we demonstrate how algorithm complexity directly increase the CPU strain. And for overall takeaway, combining synthetic benchmark and custom assembly test will reveal true system capacity and pinpoint bottlenecks.
Through this project, I gained hands-on experience in CPU benchmarking and hardware testing. I learned how different CPU handle workloads and how tools like CPU-Z and Geekbench help bridge the gap between specs and real-world performance. Working in the teams also improved my understanding of scheduling and result analysis. Overall, this project made me more confident in evaluating systems beyond just numbers.
Participating in this project has been a very insightful and valuable experience. So I get to experience and learn hands-on using the free benchmarking tools such as CPU-Z, Geekbench, Task Manager, and Minitor Partition Wizard. So I get to understand more about my laptop's capabilities, strengths, and limitation. Overall, this project has made me aware of how to evaluate a laptop, not just from the specs, but on how it performed as well in the action.
Through this project, I gained a clear understanding of my laptop overall performance, including the CPU, GPU, RAM, and storage. And also, benchmarking helped me learn what kind of tasks my device can handle efficiently and gave me insight into its current health. Now, I feel more confident in choosing the right software or adjusting settings based on my laptop real capabilities. That's all for me. Thank you.
For revision, I saw that being inside for prospects like speed or core count are bad at predicting real performance, the type of what matters most. And for example, a median CPU handled normal tasks fine, but lagged badly under heavy loads despite having enough RAM. And then I learned to focus on balanced hardware for specific jobs, like SSD for this task, multi-core for parallel work, and so on. I learned that benchmarking revealed hidden issues like fluid writes that specs couldn't show. That's all.